Okay, so in this video, we are gonna deal with the theorem in model algebra or in abstract algebra. So, we are gonna see a theorem in abstract algebra. Okay, so let me write the statement first. The theorem says a group G not equal to E, singleton E, does not have a proper subgroup if and only if G is a cyclic group of prime order. Okay, so this is the statement of the theorem. A group does not have a proper subgroup if and only if it is a cyclic group of prime order. So you can notice this if and only if here. So this is a necessary and sufficient condition. We're gonna first assume one part and we're gonna prove the other part, and then we're gonna go the other way around also. So in this proof, I'm gonna first assume let G be a cyclic group of prime order, and I will be proving it doesn't have a proper subgroup, and then I will be assuming a group does not have a proper subgroup, then I will be proving G is a cyclic group of prime order. So that is how the proof is going to go about. So here before even moving to the proof, here we have another word called cyclic. A cyclic group, what do we mean by cyclic group? It is a group, it should have a generator. Generator is an element where if you have an element A in G such that if it generates, cyclic group generated by A is equal to G, then G is said to be cyclic. Have this in your mind. Let me now start with proving the theorem. Okay, so let me first assume, one second, yeah. Let G be a cyclic group of prime order. Okay. So let me also take let H be a subgroup of G. What should I actually prove? I have to prove G does not have a proper subgroup. So I have randomly taken a subgroup of G. So if I can tell this H is never proper, then I can tell G does not have a proper subgroup. So now I'm gonna compare the order of H and the order of G. Is there any relationship between these two? Yes. Order of H will divide order of G. This is by Lagrange theorem. According to Lagrange theorem, this order of H should divide order of G whenever G is a finite group. So now, what about the order of G? Order of G is a prime number, no? So let it be like P. It divides a prime number where P is a prime number. So when will some number divide the prime number, or we can ask like this: what are all the divisors of the prime number? The only divisors of the prime number is either 1 or itself. Therefore, order of H is either 1 or P. Therefore, if order of H is equal to 1, then H is equal to singleton E. If order of H is equal to P, then H is equal to the entire group G. So now we have randomly taken a subgroup H. At last we proved that it is either is equal to E, singleton E, or it is equal to the whole group G, which means that both these groups are improper subgroups, which means a subgroup of G can never be proper. Why? Because I have randomly taken a subgroup that eventually ends up boils down to having an improper subgroup. That means it doesn't possesses a proper subgroup. Therefore, the one part is over. We have assumed G is a cyclic group of prime order. Now we proved that G does not have any proper subgroups. The other part is I'm going to assume, conversely, let me assume, let G does not equal to E, right? Does not have a proper subgroup. So this is my assumption. Now let me prove it is cyclic and then does not have a proper subgroup. So sorry, it is cyclic and prime order. My claim is G is cyclic and prime order, and it is of prime order. So this is what I'm gonna prove. So suppose G is not cyclic. I have to prove G is cyclic. So what will happen if G is not cyclic? Suppose G is not cyclic. Then for whatever element you take from G, it will not be equal to the entire group G because G is not cyclic. And so what I'm gonna do is I'm gonna take, since G is not equal to singleton E, there will be an element other than E. So let me take an element other than E in G and consider the cyclic subgroup generated by E. Therefore, this is not equal to singleton E also, no? So for whatever the element, the cyclic group generated by A is not equal to G because G is not cyclic. And so I have already also taken A is not equal to E. Therefore, the cyclic group generated by A is not equal to E as well. Which means this cyclic subgroup generated by A is a subgroup of G that is not equal to singleton E and G, which means it is not proper. Sorry, this is proper. It is a proper subgroup of G. So is it a contradiction? Yes, it's a contradiction because we have assumed G does not have a proper subgroup. Now we are here to find out the cyclic group of A, cyclic group generated by A is a proper subgroup. This happened because I assumed G is not cyclic. Therefore, G has to be cyclic. Therefore, G has to be cyclic. Right? This we got because contradiction we got because we have assumed G is not cyclic. Therefore, G has to be cyclic. Okay, so now we proved G is cyclic. Now we also have to prove G is of prime order. So let me first consider what happens if G is of infinite order, right? If G is of infinite order, then we cannot even talk about prime. So now let us also explore the possibility of having G to be of infinite order. Okay, so now let me assume G is an infinite order. Let me also take A not equal to E in G. Right? So now consider the cyclic subgroup generated by A. And maybe A square shall we consider? Yes. So let me consider cyclic subgroup generated by A square. Okay. So A will definitely be not there in cyclic subgroup generated by A square. And moreover, this will be a subgroup of G. Right? And what you can tell here you can tell A is not there in A square and it is not actually equal to G also. Therefore, this is subset of G. And I'm gonna also take whenever here itself I have taken A is not equal to G E. Therefore, the cyclic subgroup generated by A square is not equal to singleton E also. So, which means I have this subgroup A square to be a proper subgroup of G because A will never be in this cyclic group and this A square that is also not equal to E, right? Therefore, this is again a contradiction. Why am I telling this A does not belong to the A square? Because there will be no stage where we have repetitions occurs because G is of infinite order. G has n number of elements. It has so many elements, right? More than n. So now this A square it is generated by A square. That is the first element will be A square. Second element will be A square dot A square, and third element will be A square dot A square dot A square, and so on. So it will contain a square, a power 4, a power 6 and so on. So definitely A is not an element of G. And will the process end somewhere? It will never end because G is of infinite order. So this is a contradiction because we end up with the proper subgroup, and we have assumed G does not possess a proper subgroup. So why are we ending with the contradiction? Because of the fact that we assumed the order of G is infinite. Therefore, order of G is not infinite; it is a finite order. G is of finite order. Okay, now we have G is of finite order. Right? Okay, we have already proved G is cyclic. Okay, so finite in the sense that I'm going to take let order of G is equal to n. And finite can be prime, it can be composite. Right? So I have to prove it is a prime. So suppose n is not prime. This is what I'm assuming. Suppose n is not prime, which means it is composite. Therefore, n can be written as some p into q, where I can write like this. No, this is possible for all composite numbers. So 1 less than p less than n and 1 less than q less than n. I have written n as a product of p and q, where both p and q lies between 1 and n, never equal to 1 and n. And yeah, so now I'm gonna take an element in G. I've taken an element that is in G. I'm gonna also take this element is not equal to such an element. I'm gonna take from G, and I'm gonna consider a power p, right? A power p also will definitely be there in G. So now consider the cyclic subgroup generated by a power p. Right? So this will be a cyclic subgroup. This is of course a cyclic subgroup of G. Okay, so yeah. So now what about order of this particular group? Order of the cyclic subgroup. So now listen. What about a power p? Order of the particular element a power p. So the order of a power p, I would say order of a power p is q, because a power p when it rises to the power q is equal to a power pq, and a power pq is n, and a power pq is n, and n is order of g. A power order of g is e. Therefore, order of p, a power p is equal to q. Why? Because a power p, the element a power p, when it is raised to the power q, it gives me identity element, right? So I can tell order of a power p. I cannot tell order of a power p is exactly q, but I can tell order of a power p is less than or equal to q, because order should be the least positive integer such that a power that number should be equal to e. So here I have a power p, the whole power q is equal to e, which means a power p when raised to the power q gives me the identity element, but I am not sure whether this q is the least positive integer. Therefore, order of a power p is less than or equal to q. And we also know that order of the cyclic group generated by a power p is same as order of a power p, and that is less than or equal to q. So now what do we have? We have order of a subgroup, right? Consider this is a subgroup. Order of a subgroup is less than or equal to q. And if you compare q and n, q is again less than n, which means that order of a power p, the cyclic generated by a power p, is less than n, and we also know that this a power p is not equal to singleton e, because a is not equal to e. Therefore, order of a power p is greater than 1 and less than n. It is greater than 1 and less than n, which means this particular subgroup a power p is a proper subgroup of G. It's a proper subgroup of G. And this is a contradiction because we have assumed G does not have any proper subgroups. Why are we arriving at a contradiction? Because we have assumed n is a prime number. Therefore, n cannot be a, we have assumed n as not prime. That is n is a composite number. We are arriving at a contradiction. Therefore, n cannot be a composite number. N has to be prime number. So what did we prove? We have proved G is cyclic. In addition to that, we have also proved G is finite order. Now we proved G is a prime order. So combining everything, we can write, we have proved G is a cyclic group of prime order. This is what we proved, assuming G does not have any proper subgroups. Yeah, so that's it.